This talk is to present our CSCW 2020 paper, Explainable Active Learning, towards explanation as interfaces for machine teachers. We look at the task of active learning. A common bottleneck in developing machine learning application is the challenge to obtain label data. Active learning mitigates the labeling burden by having the model taking control of data and selectively querying labels from an annotator. Active learning has been a vivid research area. There is a common view of seeing the annotator as an oracle being mechanical queried and providing error-free labels. So the training process can be easily simulated without real user studies. But people are not oracles. Human errors are inevitable and can be impacted by a test setup. An effective algorithm should take into account these behavioral patterns. More importantly, this is not a pleasant experience for an annotator to be repeatedly queried while the model and its progress being completely opaque. These concerns resonate with the emergent perspective of machine teaching. That is, we should treat people in the loop of machine learning development as machine teachers and prioritize their productivity and mental well-being. And interactions should be intuitive as teaching in the real world. A common pattern in human teaching is to ask students to explain his or her answer so that teacher can gauge the student's understanding, close the gaps, and also adjust the teaching strategies. Inspired by this pattern, we propose a new training paradigm, Explainable Active Learning, in which we introduce technique from the field of explainable AI. In each interaction, the model presents its own prediction and explanation and solicits feedback from the teacher. For example, we conducted a case study to train a machine learning model that classifies customers in a database into high or low income group. With vanilla active learning, the model will select the customer and ask the annotator to give a label. With explainable active learning, the model gave its own prediction and explanation and solicited the annotator's feedback. For the case study, we chose to present a local explanation with feature importance, which is a popular technique in explainable AI. It explains by how the model weighs the feature of the instance to arrive at a prediction. Their model considers never married to be a negative indicator of personal income and predicts this unmarried customer to be in the low income group, which might very well be a flawed prediction or reasoning that teacher needs to correct. We conducted a formative study to inform the development of new algorithm and system design for explainable active learning. With a limited time, I'll skip study detail, but give an overview of the research questions and answers. Our control study compared explainable active learning and vanilla active learning in both the annotation outcome and annotator experience. Another important point we address is the mediating effect of certain individual differences. That is, whether explainable active learning benefits certain group of people more than others. We find that explainable active learning has both benefits and potential drawbacks. While we did not see significant difference in model performance, we find the explanation had an anchoring effect for low performers, people who are not as good with the income prediction task to begin with. They had a tendency to agree with the model's prediction when explanation were presented, even if the model was erroneous. For annotator experience, we demonstrated that explanation could help annotator calibrating their trust in whether the model is ready to be deployed, so they know when to stop teaching with confidence. To our surprise, explanation decreased task satisfaction, but only for those identified as having low need for cognition, according to style factor that basically indicates whether someone enjoys thinking activities in general. It also added to cognitive workload, but only for those experienced in AI and could have deeper engagement with model reasoning. Another primary goal of the experiment is to gather what kind of feedback people naturally want to give when seeing explanations. We conducted content analysis on people's open form feedback and summarized a list of feedback that feature importance-based explanation could solicit. Our current work focuses on developing new active learning algorithms that incorporate such feedback as training signals. Here is a summary. I'd like to thank you for your attention, and I'm happy to take questions.